On the 10th of April, 2019, the same image appeared on screens in Washington, Brussels, Santiago, Shanghai, Taipei, and Tokyo at the same moment. It was a ring of orange light wrapped around a circle of pure darkness. The darkness was about the width of our entire solar system, and it sat at the heart of a galaxy called M87, 55 million light-years from Earth. The light had left it before there was any human life form on Earth. For most of the previous century, no one had ever seen such a thing, and a great many serious people doubted one could exist at all. The data that built this picture was too large to send across the internet. It was recorded onto stacks of hard drives at telescopes scattered from Hawaii to the South Pole. And the drives were loaded onto airplanes and flown to 2 rooms, one in Massachusetts and one in Germany, where the pieces were slowly fitted together. The picture was real. The question this video asks is how anyone became certain of that, long before the photograph existed. If the mysteries that reach us from space are the kind of thing you like to sit with, that is what this channel is for. And subscribing is the easiest way to let the next one find you. That is the only such request you will hear. Everything after this is the story itself. The announcement happened at 6 simultaneous press conferences, timed so that the image went up in each city at the same instant, early afternoon in Brussels, late evening in Taipei. The team had kept the result quiet for nearly 2 years while they checked it. 4 independent groups had been given the same data and told to build an image without consulting one another, so that if all 4 produced a ring, the ring could not be a shared assumption smuggled in by a single method. All 4 produced a ring. The astronomer who had led much of the imaging work, Shepard Doleman, described the moment of seeing the 4 results agree as the point at which disbelief became impossible. Many of the people in those rooms had spent the better part of their careers on instruments that might have shown them nothing at all. It is worth being precise about what the photograph actually shows, because it is easy to misread. The bright ring is not the black hole. The black hole emits no light at all. What the ring shows is hot gas, orbiting close to the object and glowing fiercely as it does so, bent into a circle by the gravity of the thing at the center. The dark patch in the middle is the shadow of the black hole cast against that glow. It is larger than the object that casts it, because the gravity bends the paths of light inward, wrapping the darkness in a halo that is brighter on one side than the other. That asymmetry is not an accident of the camera. It is the gas on one side of the ring rushing toward us, and the gas on the other side rushing away, one side brightened and the other dimmed by its motion. The picture, in other words, is not a portrait. It is a measurement. The object at the center has a name that looks like a typographical error. It is called M87, with a small star symbol after it, written M87 star and pronounced M87 star. The star symbol is the convention astronomers use for the black hole at the center of a galaxy, to distinguish it from the galaxy as a whole. M87. The galaxy is enormous, one of the largest within reach of our telescopes, a swollen elliptical cloud of perhaps 1 trillion stars sitting at the heart of the Virgo cluster. M87 star, the black hole, sits at its very center, and it is large even by the standards of such objects. It contains roughly 6.5 billion times the mass of the Sun. If it were placed where our Sun is, its shadow would swallow the orbits of all the planets and reach well beyond them. M87. The galaxy was, in fact, one of the first objects in the sky to hint that something very strange lived at its center, long before anyone spoke of black holes. In 1918, an astronomer named Heber Curtis, working at the Lick Observatory in California, noticed a thin straight ray of light projecting out from the galaxy's core, and recorded it in his notes as a curious straight ray connected to the nucleus. He had no way of knowing what he was looking at. We now know it as a jet, a beam of matter flung outward from the immediate surroundings of M87 star at very nearly the speed of light, reaching some 5,000 light-years out into space, far beyond the galaxy's bright center. A single black hole, dark and silent by its own nature, was driving one of the most powerful sustained outflows of energy known in the nearby universe. That paradox, an object that gives off no light powering a beam visible across millions of light-years, is one we will be able to resolve later. For now, it is enough to notice that the center of M87 had been quietly announcing itself for 100 years before anyone managed to photograph what sat there. And yet, across 55 million light-years, it appears in our sky as something almost unimaginably small. Capturing it was the equivalent of standing in New York and reading the date on a coin lying on a table in Los Angeles, or of photographing a single orange placed on the surface of the moon. No single telescope on Earth could do it. To see something that small at that distance, you would need a telescope as wide as the planet, so the people who took the picture built one. They did it by linking radio dishes already scattered across the world, in Hawaii, in Arizona, in Mexico, in Chile, in Spain, and at the South Pole, and pointing them all at the same patch of sky on the same nights in April 2017. Each dish recorded the radio waves arriving at its location, stamped with the time from an atomic clock accurate to better than a second in 100 million years. Separately, none of these recordings meant much. Together, timed precisely against one another, they could be combined as though they were fragments collected by the surface of one vast dish the size of the Earth itself. This technique has a name, very long baseline interferometry, but the idea behind it is simpler than the name. If you cannot build a telescope as big as the world, you can borrow the world's width by spreading smaller telescopes across it and synchronizing them with exquisite care. The amount of data this produced is difficult to convey. Over a few nights, the array recorded several thousand trillion bytes of information, far too much to transmit electronically. It was written instead onto roughly 1,000 hard drives, and those drives were physically shipped to central sites to be processed. The drives from the South Pole could not be flown out until the Antarctic winter ended, so part of the picture of M87 star spent months waiting for the weather. When the data finally came together, it still did not form an image on its own. It had to be reconstructed, carefully and skeptically, by people who knew exactly how badly they wanted to see a ring and were determined not to fool themselves into seeing one that was not there. We will return, at the end of this video, to how they guarded against that temptation, because it is one of the quietest and most admirable parts of the whole effort. For now, hold on to the central strangeness of the achievement. A photograph was taken of an object from which, by definition, no light can escape. That sounds like a contradiction, and understanding why it is not is a large part of understanding black holes at all. You cannot photograph the thing itself. You can only photograph the absence it creates, outlined by everything around it that still shines. The image of M87 star is a picture of a silence made visible by the noise surrounding it. What makes all of this remarkable is not only the engineering. It is that the object was predicted in something close to its true form, more than 100 years before anyone confirmed it was there. The shadow in that photograph has a size, and that size was calculable in advance. Knowing only the mass of the central object, the physics worked out in the early 20th century tells you exactly how large the dark circle should appear. When the measurement came back, the shadow was the size the equations said it would be. A prediction made with pencil and paper in 1915, and the years just after had been waiting, patiently, for the technology to catch up to it. Black holes did not arrive in human understanding as a discovery in the usual sense, the way a new continent or a new species arrives, found first and explained later. They arrived the other way around. They appeared first as a consequence, an answer that fell out of a set of equations describing gravity, An answer so extreme that the man who wrote the equations did not believe it described anything real. For decades, the idea lived only on paper, regarded by most physicists as a mathematical curiosity, a flaw perhaps, a place where the theory said something absurd and was therefore probably being misused. The history of black holes is, for a long stretch, a history of intelligent people trying to explain why these things could not possibly exist. The doubt was not foolishness. It came from a reasonable instinct that nature does not usually permit its quantities to run off to infinity. The equations, taken at face value, said that if you compressed enough matter into a small enough space, the pull of gravity at the center would climb without limit, and the fabric being described would, in some sense, tear. To most physicists, an answer like that was not a discovery about the world. It was a warning sign that the theory had been pushed past the point where it still applied, the way a weather forecast stops meaning anything if you ask it about 1,000 years from now. Surely, they reasoned, some other effect would intervene before matter ever reached such a state. Surely a real star, made of real material, would find some way to hold itself up. For a long time, that was the respectable position, and the people who held it were not careless thinkers. They were being appropriately suspicious of a result that seemed too extreme to be true. What changed their minds, eventually, was that the universe kept producing the result anyway. They were wrong, and the way they came to understand they were wrong is a genuinely beautiful sequence of reasoning and observation, carried out across 3 generations. It runs from a theory written in wartime, through a solution found by a man dying in the trenches, through a young student's calculation made on a long sea voyage, to a star in our own galaxy whose motion gave the game away, to a tremor in the shape of space, recorded by machines tuned to listen for it, and finally to that ring of light on 6 screens at once. To follow it, we have to start where the people who first stumbled onto black holes started. Not with darkness and not with collapse, but with gravity, and with a particular puzzle about gravity that had been sitting unresolved for more than 200 years. The man who took it up did not set out to find black holes. He set out to understand why things fall. The answer he found was so much stranger than the question that it took the rest of the century to absorb it. And black holes were only the most extreme of the strange things it turned out to contain. Before the photograph, before the hard drives and the atomic clocks, before the doubt, there was that one idea about falling. It is where we have to begin, because everything else, including the darkness at the center of M87, follows from it. And the person who finally cracked it had been told, as a young man, that he had no particular future in physics. His name was Albert Einstein, and the assessment was not entirely unfair at the time. He had finished his physics degree in 1900 near the bottom of the group cleared to teach. He had irritated the professors whose recommendations he needed, and he spent the years that followed not at a university, but at a patent office in Bern, examining applications for electrical devices 6 days a week. It was there, at a clerk's desk, that he did the work that would eventually overturn the oldest and most successful theory in all of physics. The theory he was about to revise had stood, essentially unchallenged, for more than 200 years, and it had been built by the one predecessor whose reputation rivaled the one Einstein would acquire. Isaac Newton had published his account of gravity in 1687, and as a description of how things move, it was very nearly perfect. It explained the fall of an object and the orbit of the moon with the same single rule. It let astronomers predict eclipses centuries in advance and weigh the planets without leaving the ground. When a new world, Neptune, was discovered in 1846, it was found because Newton's law said something massive had to be tugging on Uranus from a particular patch of sky, and a telescope pointed there found it within a degree of the prediction. A theory does not get more triumphant than that. The famous story has the idea arriving with a falling apple in Newton's garden, and while the apple may be partly legend, the leap it stands for was real and genuinely radical. The same pull that brought the apple down, Newton proposed, reached all the way to the moon and held it in its orbit. Earthly falling and heavenly motion, which everyone before him had treated as separate kinds of thing, were one phenomenon obeying one law. That unification is what made the theory so commanding, and it is also what made the hole at its center so easy to overlook. But Newton's law, for all its power, came with a confession buried inside it, and Newton himself was the one who made the confession. His law said how strong gravity was, but it said nothing whatever about how it worked. The sun pulls on the Earth across 93 million miles of empty space. How? Through what? Newton's equation reached across that gap instantly, with nothing in between to carry the pull, and Newton admitted in a letter that the idea of one body acting on another at a distance through empty space, with no medium between them, was to him so great an absurdity that he did not believe any competent thinker could accept it. He had written the law down because it worked. He had no idea why it should. For 200 years that gap sat there, politely ignored, because the predictions were so good that the missing explanation felt like a philosophical detail. Einstein could not ignore it, and the thread he pulled to unravel it was not the orbit of a planet, but something far more ordinary, a thought he later called the happiest of his life. It occurred to him, around 1907, that a person falling freely does not feel their own weight. Today, we have all seen this without recognizing it, in the footage of astronauts drifting inside an orbiting station. They are not beyond gravity. The Earth pulls on them almost as strongly as it pulls on us. They float because they and their spacecraft are falling together, around and around the planet, and in free fall, the sensation of weight simply vanishes. Einstein turned that ordinary fact into a key. Imagine, he said, a person in a sealed room with no windows. If that room sits at rest on the ground, the person stands on the floor with their normal weight. Now imagine the same room far out in empty space with a rope attached to the top, being pulled steadily so that it accelerates. The floor rushes up to meet the person's feet, pressing against them exactly as the ground does. Inside the sealed room, Einstein argued, there is no experiment the person could perform to tell the two situations apart. The pull of gravity and the push of acceleration are not merely similar. They are, as far as anyone inside can ever determine, the same thing. From that single equivalence, one consequence follows that Einstein seized on early because it offered a way to test the whole idea. Imagine a beam of light crossing the accelerating room from one wall to the other. In the time the light takes to cross, the room has sped up, so the far wall has moved, and the beam strikes a little lower than where it started. To the person inside, the light has bent downward along a faint curve. But if acceleration and gravity are truly the same, then gravity must do to light exactly what acceleration does. Light passing a massive body must bend. This was a remarkable thing to claim because light was thought to be weightless, the one thing gravity should have no grip on at all. Newton's picture offered no clear reason for a ray of starlight to swerve as it grazed the sun. Einstein's picture demanded it, and even specified by how much. Light, like everything else, simply follows the shape of space, and near a heavy enough object, that shape is curved. Keep that demand in mind. The bending of light is the hinge on which both the proof of the theory and the very existence of black holes would later turn. This is a stranger claim than it sounds, and Einstein spent 8 years working out where it led. The mathematics he needed did not yet exist in a form he could use, and he was, by his own admission, not a natural mathematician. He leaned heavily on an old friend, Marcel Grossmann, who steered him toward the geometry of curved surfaces that had been developed decades earlier for entirely abstract reasons, with no thought that it might one day describe the universe. There were years of false starts. At one point, Einstein convinced himself the whole approach was wrong, and abandoned a nearly correct version of the equations for 2 years before returning to it. In the final weeks of 1915, racing a brilliant mathematician named David Hilbert, who was closing in on the same result, he worked himself to exhaustion and arrived at the finished equations. If gravity and acceleration are genuinely indistinguishable, then gravity cannot be a force reaching across space in the way Newton imagined. It has to be something about the stage on which everything moves. And the conclusion he arrived at, in the autumn of 1915, was that mass bends the very geometry of space and time around it, and that what we feel as the pull of gravity is simply objects following the straightest possible path through a space that has been curved. The usual picture offered for this is a heavy ball resting on a stretched rubber sheet, sinking into it and making a dip, so that a marble rolled nearby curves inward toward the ball. The picture is useful and also slightly misleading because it explains gravity using gravity. The ball sinks because the Earth is pulling it down into the sheet. So hold the image loosely. What it gets right is the essential idea. Matter does not reach out and grab. Matter tells the space around it how to curve, and that curved space tells everything moving through it how to travel. The Earth orbits the Sun, not because a rope of force connects them, but because the Sun has put a deep, smooth valley into the shape of space. And the Earth is rolling around the inside of that valley along the straightest path available to it. There is no pulling. There is only the shape of things, and motion following the shape. Time belongs to this picture too, and that turns out to matter enormously for black holes. Einstein's theory does not bend space alone. It bends space and time together as a single fabric, and a clock deeper in a gravitational valley runs measurably slower than a clock higher up. This is not a trick of perception or a fault in the clocks. It is the rate of time itself differing from place to place, depending on how curved the space around it is. The effect is tiny near the Earth, but it is real and it is measured every day. The satellites that provide navigation signals carry clocks that tick slightly faster than clocks on the ground, because they sit higher in Earth's gravity. And if that difference were not corrected for, the positions they report would drift by kilometers within a day. Every time a phone finds its location, it is quietly confirming that gravity slows time. When Einstein finished in November of 1915, he had a set of equations, 10 of them woven together, that related the amount of mass and energy at any place to the precise way space and time curve there. The equations are compact to write and ferociously difficult to solve, but their meaning can be put in a single sentence that has become the standard summary. Matter tells space how to curve, and curved space tells matter how to move. Each side governs the other endlessly, and out of that two-way conversation comes everything from a falling apple to the orbit of a galaxy. A new theory, however elegant, is only worth as much as its predictions, and Einstein had one waiting. There was a small, stubborn flaw in the heavens that Newton's law had never been able to mend. The planet Mercury, closest to the Sun and most deeply sunk in the Sun's gravity, does not trace exactly the same ellipse year after year. The whole orbit slowly rotates, its closest point to the Sun creeping forward over the centuries. Most of that creep could be explained by the tugs of the other planets, but a small residue could not, an extra advance of about 43 seconds of arc per century, a sliver of an angle so fine that it had taken decades of careful observation to pin down. Astronomers had searched for an unseen planet closer than Mercury to account for it. None was ever found. Einstein took his new equations and calculated how Mercury should move through the curved space near the Sun, with no extra planet, no adjustment, nothing added to make the numbers fit. The orbit, his theory said, should rotate by an extra 43 seconds of arc per century. It matched the unexplained residue almost exactly. He later told a friend that the discovery gave him heart palpitations, that for a few days he was beside himself with joy. He had not designed the theory to explain Mercury. The explanation simply fell out of it, the way the size of the shadow in a certain photograph would fall out of it 100 years later. So the picture was not a guess. By the end of 1915, there were real equations, tested against a real planet, describing a universe in which space and time were not a fixed, empty stage, but a flexible fabric, shaped by everything within it. And it was precisely this success that set the trap. Because if mass curves space, then a question follows immediately, a question that is almost childishly simple to ask, and that turned out to have a monstrous answer. What happens if you keep concentrating mass into a smaller and smaller space? How deep can the valley get? Is there a limit to how far the fabric can bend before something gives way? Einstein does not seem to have rushed to ask it. The equations were new, the world was at war, and merely getting the theory understood was work enough. He assumed, reasonably, that exact solutions to his ferocious equations would be a long time coming, perhaps the slow labor of many mathematicians over many years. He was wrong about that. The first exact solution arrived within weeks, in a letter, and the man who sent it was not at a desk in a university. He was a serving artillery officer, computing the curvature of space by hand in the gaps between bombardments on the Russian front of the First World War. And folded inside his tidy, elegant solution, though almost no one recognized it at the time, was the first clear mathematical description of a black hole. The officer's name was Karl Schwarzschild, and he was already one of the most respected astronomers in Germany when the war began. He was director of the observatory at Potsdam. He had done important work in fields ranging from the orbits of comets to the behavior of light in the atmosphere. And he was past 40, well beyond any obligation to serve. He volunteered anyway, and by 1915 he was stationed on the Eastern Front, calculating the trajectories of artillery shells for the German army. When Einstein's new theory of gravity reached him, almost certainly through the published proceedings of the Berlin Academy, he read it between his military duties and set himself a problem in the little time he had. He chose the simplest case he could imagine. Forget the messy real universe with its many bodies tugging in all directions. Take a single sphere of mass, perfectly round, sitting alone in space, not spinning, not changing. What exactly does Einstein's curved space look like around an object like that? It was the most basic question one could ask of the new theory, and Einstein had expected it to resist solution for years. Schwarzschild solved it in a matter of weeks, exactly, with the curvature described by a clean formula, and he mailed the result to Einstein in December of 1915. Einstein was astonished. He replied that he had not expected the problem to be answered so simply, and he presented Schwarzschild's solution to the Academy on his behalf. It was the first exact solution of the field equations, and it remains the most important one ever found. It is worth pausing on how unusual the situation was. Einstein had presented his complete theory of gravity to the Berlin Academy on the 25th of November 1915. Schwarzschild's letter arrived just over a month later. A solution that Einstein had thought might take years to construct had been produced by a serving officer in an active war in a matter of weeks, on the basis of a paper that had only just been published. It is a small reminder that the people working at the frontier of physics in those years were not numerous, and they read each other's papers carefully and quickly, even across enemy lines. Schwarzschild's letters from the front contained, in addition to the geometric solution, his calculations on the spectra of stars and his theoretical work on quantum effects in radiation, none of which had any direct relation to his military duties. He had carved out the work in moments stolen from a routine of artillery direction and the slow approach of a disease that would soon kill him, and in those moments, he had managed to give the new theory of gravity its first concrete object. Within Schwarzschild's tidy formula, however, there was something peculiar, and he noticed it himself. The equation behaved normally as you moved through the space around the mass. But at one particular distance from the center, it did something alarming. Certain terms in it blew up. One quantity shot to infinity and another dropped to zero. And the smooth description of space seemed to come apart at that radius, as though the map had a tear running around a perfect circle at a fixed distance from the center. For an ordinary object, the warning was harmless, because that critical distance lay far inside the body itself, buried deep within the sun or the earth, where the formula for empty space did not apply anyway. For the sun, the critical radius worked out to under 2 miles, and the sun is nearly 900,000 miles across. So the troublesome circle sat deep in the interior and meant nothing physical. For the Earth, the radius was smaller still, about the size of a small marble. As long as no object was ever squeezed smaller than its own critical radius, the strange circle stayed safely hidden and could be dismissed. But the radius existed for any mass. Every object had one, a specific distance, fixed entirely by how much mass it contained. And the formula was perfectly clear about what it meant. If you could ever compress an object until all of its mass fit inside that critical radius, the tear would no longer be buried in harmless interior. It would be exposed, out in the open space around the collapsed mass, and at that boundary, the equation said that the curvature of space became so extreme that nothing crossing inward could ever come back out. Not matter, not light. The valley in the fabric would have become a shaft with no floor and no way back up. That critical distance is now called the Schwarzschild radius, and the surface it traces is the event horizon, though neither name nor the full understanding existed yet. Schwarzschild had written down, in the first months of the theory's life, the precise size of a black hole of any given mass. It is worth pausing on how small these radii are, because the smallness is the whole reason the idea seemed absurd. The rule is simple: the more mass, the larger the radius, in direct proportion. The Sun, with its third of a million Earth masses, has a Schwarzschild radius of under 2 miles, meaning you would have to crush the entire Sun down to a ball you could drive across in minutes before it disappeared behind its own horizon. The Earth's radius is about that of a marble, perhaps a third of an inch. A human body's Schwarzschild radius is so small that there is no honest way to picture it, vastly smaller than a single atomic nucleus. Nothing in ordinary experience comes remotely close to being that compressed. This is exactly why the strange circle seemed safely theoretical. To expose it, nature would have to do something to matter that no known force could accomplish, packing a star's worth of material into the volume of a city, or a city's worth into nothing at all. The equations permitted it. Common sense refused it. The disagreement between those two would take half a century to settle. He did not live to see what he had found come to be believed. On the front, he contracted a rare and painful autoimmune disease of the skin, was sent home gravely ill, and died in May of 1916, only months after sending Einstein the solution that carries his name. He was 42. The mathematics outlived him by a century and now describes objects photographed across tens of millions of light years, but he had no way of knowing that the circle in his equations corresponded to anything real. Almost no one thought it did. For now, the strange radius was set aside as a curiosity, and attention turned to the test that would make or break the entire theory, the test that hinged on the bending of light. Einstein had predicted that starlight grazing the edge of the sun should be deflected by a specific small angle, very nearly twice the amount that a naive application of Newton's gravity might suggest. The trouble was that the sun is overwhelmingly bright, and the stars whose light would pass closest to it are invisible in the daytime glare. There was only one circumstance in which those stars could be seen with the sun directly among them, and that was during a total eclipse, when the moon blocks the sun's disk and the sky around it darkens enough for stars to appear. The English astronomer Arthur Eddington took up the challenge. A total eclipse was due on the 29th of May, 1919, and Eddington organized 2 expeditions to observe it, one to the island of Principe off the west coast of Africa, and one to Sobral in Brazil. The plan was to photograph the stars clustered near the eclipsed sun and compare their apparent positions with their ordinary positions months later, when the same stars were visible at night with the sun far away. If the starlight bent, as Einstein said, the stars near the sun's edge would appear nudged very slightly outward from their true positions, shifted by the sun's curving of the space their light crossed. The shift to be measured was about 1/2000th of a degree, at the very limit of what the photographic plates of the time could resolve. There was a quiet drama in the timing that is easy to miss. Eddington was English, Einstein was German, and the 2 countries had just spent 4 years killing each other's young men by the million. An Englishman crossing the world to test and perhaps confirm the theory of a German in the immediate aftermath of that war was not a neutral act. Eddington, a Quaker and a pacifist, seems to have regarded the reconciling power of the gesture as part of its point. The clouds nearly ruined it. On Principe, the morning of the eclipse was rainy, and the sun broke through only in the final minutes. Eddington came away with a small number of usable plates. When the measurements were finished and the positions compared, the starlight had shifted, and by close to the amount Einstein's theory required, not the smaller Newtonian figure. Eddington announced the result at a joint meeting of the Royal Society and the Royal Astronomical Society in November of 1919. The reaction went far beyond the usual circulation of a scientific finding. The Times of London carried the news, and within days Einstein, until then known mainly within physics, had become the most famous scientist in the world, his name attached in the public mind to a universe in which space and time could bend. The theory had passed the test it most needed to pass. Gravity bent light by the predicted amount, and the curved space picture was no longer one option among several. It was how gravity worked. Historians of science have since picked over Eddington's plates with great care, and the picture is a little less clean than the triumphant headlines suggested. The expedition produced 3 sets of photographs of differing quality, and one set, taken with a telescope that had apparently been distorted by the heat, gave a result closer to the smaller Newtonian deflection. Eddington set that set aside as unreliable and reported the other 2, which favored Einstein. His judgment about which plates to trust has been defended by later analyses, and modern repetitions of the eclipse measurement have confirmed Einstein's value many times over, with far better instruments, so the conclusion was right. But the episode is a useful reminder that even a famous confirmation is rarely a single clean moment. It is a human act of judgment about messy data, made by people who, like the imaging teams nearly a century later, had to be careful not to let their hopes choose their results for them. And here is the irony that sits at the center of this part of the story. The very same theory, now triumphantly confirmed by the bending of starlight, also contained Schwarzschild's strange radius, the boundary past which light would not merely bend, but be trapped entirely. The physics that everyone now accepted, that had made Einstein a household name, implied the possible existence of objects from which no light could escape. Yet for decades, almost no one took that implication seriously as a description of anything that could actually form in nature. The theory was embraced. Its most extreme consequence was quietly walled off. The resistance had a respectable basis, and Einstein himself shared it. The objection was not really about the mathematics, which no one disputed. It was about whether nature would ever actually drive matter into such a state. A solution describing what happens if all the mass fits inside the critical radius is only relevant if something can squeeze mass that far, and every familiar object resists being squeezed. Push on a rock, and it pushes back. Compress a gas, and its pressure rises to oppose you. Stars hold themselves up against their own enormous gravity by the outward push of the heat and pressure generated in their cores. The universe seemed full of forces that resist compression. Why should anyone believe that any of these defenses could fail so utterly that a star would collapse all the way past its own Schwarzschild radius, leaving nothing behind but a region of trapped light? Surely some pressure, some resistance, some new effect would always intervene to halt the collapse before that absurd point was reached. Einstein went so far as to publish a paper in 1939 arguing, with a specific calculation, that such complete collapse could not occur, that matter would always find a stable configuration before vanishing behind the critical radius. He was, in this instance, mistaken, and the mistake is instructive. He had assumed the matter would settle into a stable orbit short of collapse, but had not fully reckoned with what happens when a star simply runs out of the fuel that generates its supporting pressure. The question of whether a real star could die in the way the equations seemed to permit was not, in the end, a question about geometry at all. It was a question about what holds a star up, and about what happens when that support finally gives way. To answer it, the story has to leave the chalkboard and go inside a dying star. And the person who first followed the collapse all the way down to its terrible conclusion did the crucial part of the work as a teenager, on a long ocean voyage from India to England, with little to do but calculate. The teenager's name was Subramanian Chandrasekhar, and in the summer of 1930 he boarded a steamship in Bombay bound for England, where he had won a scholarship to study at Cambridge. He was 19 years old. The voyage took about 2.5 weeks, and Chandrasekhar spent much of it on deck with a notebook and a problem he had been turning over in his head. The problem was about what happens to stars when they die. To understand what he found, it helps to know how a star stays alive in the first place. A star is a great struggling balance between two opposed forces. Its own gravity, the weight of all that gas pressing inward, would crush it to a point in minutes if nothing pushed back. What pushes back is the heat and pressure of nuclear fusion in the core, where hydrogen atoms are squeezed together so violently that they fuse into helium and release enormous quantities of energy. That outflowing energy generates the pressure that holds the star up. For as long as the fuel lasts, gravity and pressure stand in tense equilibrium, and the star shines steadily. Our sun has been doing this for 4.5 billion years, and has roughly the same again before it has to stop. But the fuel does run out. Eventually, a star uses up the hydrogen in its core, and then, depending on its mass, the helium that fusion produced, and then heavier elements still, working its way up a periodic table of energy sources, each one harder to ignite than the last. With each stage, the outward pressure flickers and changes, and the star swells, contracts, and sheds layers in great slow gasps. The sun, when its turn comes, will swell into a red giant large enough to swallow the inner planets, then puff its outer layers away as a glowing shell, leaving behind only the burnt-out core. That core will be roughly the size of the Earth, but containing close to the mass of the sun, made of matter so densely packed that a teaspoonful would weigh several tons on the surface. Stars in this state are called white dwarfs, and they were known well before Chandrasekhar came along. The first one identified, the small companion of the bright star Sirius, was puzzled over from the 1860s onward, and its strange density was reluctantly accepted by the 1920s as an astonishing but stable fact of nature. What held white dwarfs up was the deep puzzle. Their nuclear fuel was exhausted. There was no fusion in their cores, yet they did not collapse further. The answer, worked out in the early years of quantum mechanics, lay in a curious rule about electrons. Electrons, it turns out, refuse to occupy the same quantum state as one another. When matter is squeezed densely enough that the electrons are forced very close together, they push back not because of any familiar repulsion, but because the rules of quantum physics simply forbid them from being packed any tighter. This is called electron degeneracy pressure, and it is what keeps a white dwarf rigid against its own gravity. It is the closest thing to an absolute floor that ordinary matter has. The accepted view, before Chandrasekhar, was that this pressure could be relied on always to win. No matter how massive the burnt-out core, electron degeneracy would eventually halt the collapse, and the star would settle into a stable white dwarf. The collapse problem, in other words, had been quietly considered solved. Nature's last-ditch defense always held. Chandrasekhar, on the deck of the steamship, did what no one had quite done with the necessary care. He took into account something his elders had treated as a small correction. The electrons in a sufficiently massive collapsing core, he realized, would be moving at speeds approaching the speed of light, and Einstein's special relativity, the older theory underlying the general one, says strange things about objects moving that fast. When the calculation is redone properly for relativistic electrons, the pressure no longer rises fast enough to keep up with gravity at high enough masses. There comes a point at which gravity simply wins. The degeneracy floor gives way. By the time the ship docked in England, the young man had a number. There was a maximum mass for a white dwarf, a ceiling above which the electron pressure could no longer hold. He calculated it at about 1 4/10 times the mass of the Sun. Any burnt-out core lighter than that could rest as a white dwarf forever. Any core heavier than that had nothing to stop it from collapsing further. The limit is now called the Chandrasekhar limit, and it sits at the very center of how we understand stellar death. The reception was not gracious. Chandrasekhar pursued the work over the following years and presented his findings at a meeting of the Royal Astronomical Society in 1935 with Arthur Eddington, the same Eddington who had measured the bending of light in the audience. Eddington was by then the most influential astrophysicist alive, and he rose immediately after the talk to reject the conclusion in scathing terms. There must, he said, be some law of nature that prevented a star from behaving in this absurd way. The young Indian's mathematics was no doubt clever, but the conclusion was, as Eddington saw it, manifestly wrong. The senior man's authority effectively buried the result in mainstream astrophysics for decades. Chandrasekhar left the field for other subjects and did not return to it in earnest until the 1960s. He eventually received the Nobel Prize in 1983 for the same work the room had shouted down nearly half a century earlier. Once you accept the Chandrasekhar limit, however, you cannot escape its consequence. A burnt-out core heavier than about 1 4/10 solar masses cannot rest as a white dwarf. So what does it become? In the late 1930s, the physicists Robert Oppenheimer and George Volkoff, soon joined by Hartland Snyder, took up the question. They found a second floor. Beyond the Chandrasekhar limit, gravity could crush electrons into the atomic nuclei themselves, forcing them to merge with protons and become neutrons. The result is an object made almost entirely of neutrons, packed against one another at nuclear density. A neutron star contains as much as twice the mass of the Sun, but in a sphere only about 20 kilometers across, the size of a small city. A teaspoonful of it would weigh as much as a mountain. Neutrons, like electrons, have their own degeneracy pressure, and that pressure can support a star against gravity, up to a point. For a long time, neutron stars were as theoretical as the black holes lying beyond them. Their existence had been proposed by the astronomer Fritz Zwicky in 1933, almost as soon as the neutron itself had been discovered the year before. And like Chandrasekhar's limit, the idea was not warmly received. Zwicky had also proposed, in the same breath, that these strange, dense remnants would be left behind by the explosions of dying massive stars, the events we now call supernovae, and that proposal, too, was treated with skepticism. 3 decades passed with no observational evidence that any such object existed. Then, in 1967, a graduate student at Cambridge named Jocelyn Bell noticed a curious regular blip in her radio telescope data, a pulse repeating every 1 1/3 seconds with extraordinary precision. It was so regular that her supervisor briefly entertained, half seriously, the idea that it might be a signal from another civilization. It turned out to be a spinning neutron star, sweeping a narrow beam of radio waves across the Earth like a lighthouse, and over the next few years many more were found. The neutron stars were real. The remaining question was whether the objects past the second floor, the ones with nothing left to hold them up, were real as well. But it too has a limit. The exact value depends on details of nuclear physics that are still being refined, but it lies somewhere between 2 and 3 solar masses. Above that, neutron degeneracy fails as electron degeneracy failed before it. No known floor remains. And in 1939, in a short paper that received almost no attention at the time, Oppenheimer and Snyder calculated, using Einstein's theory directly, what should happen to a sufficiently massive collapsing star whose support has finally and completely given way. The answer was unambiguous. It does not settle. It does not find any new equilibrium. It contracts past its own Schwarzschild radius, vanishes from view, and continues to collapse, with no remaining force in physics capable of stopping it. The horizon closes around it, and the star is gone from the universe outside, except for its gravity, which remains behind as the only sign that anything is there. The strangest feature of the Oppenheimer-Snyder calculation, the one that would shape every later description of what a black hole really is, concerns time. From the point of view of an outside observer, the collapse does not actually appear to finish. As the surface of the dying star nears its Schwarzschild radius, the gravitational slowing of time becomes so extreme that, to anyone watching from a safe distance, the surface seems to creep more and more slowly, fading and reddening and asymptotically approaching the horizon without ever quite reaching it. But from the point of view of the collapsing matter itself, nothing of the kind happens. The fall continues smoothly through the horizon and onward, in a finite and rather short period of its own time. The two descriptions are both correct. They simply belong to different observers, and Einstein's theory provides no privileged perspective from which to declare one truer than the other. A black hole, in this sense, is an object whose entire history of collapse remains forever in the slowed-down outside view, while internally, that same collapse has already happened. It is one of the first hints that thinking about these objects honestly will require giving up the assumption that there is one universal clock the universe runs by. Oppenheimer and Snyder published their result the very same week that the Second World War began in Europe. The paper appeared in the Physical Review on the 1st of September 1939, the day Germany invaded Poland. Within months, Oppenheimer was being drawn into the work that would become the Manhattan Project, and physicists' attention turned overwhelmingly to other matters. The first complete description of gravitational collapse to a black hole, the keystone calculation that took the idea from a feature of the equations to a prediction about real stars, was published into a world that had something else to think about. It would be 25 years before the result was taken up again seriously. That delay had a curious side effect. By the time relativistic collapse was rediscovered in the 1960s, the language used to describe it had hardened in ways that look unfortunate now. The earlier German tradition had called these objects frozen stars, because from the outside, the collapse appears to slow as it approaches the horizon, time dilating so severely that to a distant observer, the falling matter seems to creep and freeze just above the boundary. That picture, while incomplete, has a certain accuracy about it. The American physicist John Wheeler, lecturing at a conference in 1967, used a more arresting phrase. He spoke of a black hole. The name caught on at once, and the older language disappeared. The new term was vivid and economic, and it has been the standard one ever since, though as we shall see, in some respects it understates what the object actually is. By the early 1960s, the theoretical picture had at last begun to come into focus. A sufficiently massive star having exhausted its fuel, will collapse past its own event horizon, leaving behind a black hole whose size is set entirely by its mass. The collapse is genuine and unstoppable. There is no last-minute floor. The mathematics is unambiguous, and the conditions for it to occur, a stellar core heavier than a few solar masses running out of fuel, occur all the time in our galaxy. So somewhere out there in the sky, the theorists were now saying real black holes ought to exist in considerable numbers, formed in the depths of massive stars and seeded into the surrounding space. But none had been seen. A black hole emits no light. It betrays itself only through its gravity, and finding a small dark object in the sky by its gravity alone is a task of forbidding difficulty. For the idea to move from beautiful theory to confirmed reality, somebody was going to have to catch one in the act. And what eventually gave the first one away was not the black hole itself, but the catastrophe of a companion. A luminous star tied to it by gravity and being slowly, brilliantly torn apart from a safe distance. The first hard evidence for any black hole, in other words, would come from following the light of something else, watching where it went, and noticing that some of it never came back. The hidden object would announce itself only by what it did to its neighbor, in a wavelength of light that the atmosphere of the Earth forbids us to see from the ground. A black hole, then, is not really an object in the usual sense. It is a region of space. The mass at the heart of it occupies, according to the bare reading of the equations, no volume at all, a single point of infinite density called a singularity, where the curvature of space and time becomes mathematically unbounded. Almost no physicist believes this point is literally real. The singularity is the place where Einstein's theory, our best account of gravity, says something it cannot mean. The same way an arithmetic system signals trouble by demanding that you divide by 0. The honest interpretation is that some deeper theory, one that combines gravity with quantum physics, will have to take over there and give the right answer. We do not yet have that theory. What we have instead is the region around the singularity, and it is the region, not the point, that we mean when we speak of a black hole at all. The visible boundary of that region is the event horizon, the surface at 1 Schwarzschild radius from the center. From outside, the horizon is what defines the object. It is not a wall, not a surface you would feel passing through. There is nothing locally to mark it. An astronaut falling toward a sufficiently large black hole would cross the horizon without noticing any particular event at all. No shudder, no flash, nothing. The horizon is defined entirely by what happens afterward. Inside it, every possible future path of every particle, of every beam of light, leads inward, toward the central point. There is no available trajectory that returns. Falling out is not difficult inside the horizon. It is impossible in the same sense that traveling into your own past is impossible. The geometry has simply rotated so that the direction we ordinarily call the future now points inward, and outward has become as inaccessible as yesterday. This is one of the harder things to picture, honestly, so it is worth pausing on it. Outside a black hole, you can choose to move in any spatial direction you like. You cannot, however, choose not to move forward in time. Time only flows one way. What happens at the event horizon is that the role of one spatial direction, the direction away from the center, swaps with the role of time. Inside the horizon, getting closer to the central point becomes as unavoidable as the next moment is for us. You can still move sideways. You cannot choose not to fall in, any more than you can choose not to age. To leave a black hole through its event horizon is not difficult or unlikely. It is the wrong sort of question, like asking how to escape Tuesday. The size of the horizon is set entirely by the mass within. Nothing else matters. A black hole holding 10 times the mass of the Sun has a horizon about 30 kilometers across, the size of a city neighborhood. The one at the center of our galaxy, 4 million solar masses, has a horizon about 24 million kilometers across, which sounds enormous until you compare it to the orbits of the planets and realize the whole structure would fit comfortably inside the orbit of Mercury. The one in M87, 6.5 billion solar masses, has a horizon you could nestle our entire solar system inside many times over. These are not enormous objects compared to anything else in astronomy. The supermassive black hole at the heart of M87 is smaller than its host galaxy by a factor of trillions. It is an enormous mass in a small space, not a thing of enormous extent. Outside the horizon, in the curved space around it, several features stand out, and they have practical importance because they are the regions from which the light we eventually see actually comes. The closest is what astronomers call the photon sphere, a thin shell at 1.5 times the Schwarzschild radius, where gravity is just strong enough to bend the path of a beam of light into a circle. A photon passing tangentially at exactly this distance would orbit the black hole indefinitely, in principle, before being nudged either inward or outward by the slightest disturbance. In practice, photons do not stay there long, but the photon sphere shapes what a black hole looks like, because light from material behind the hole can be bent around and emerge on our side, giving rise to the bright ring we see in pictures like the one of M87. The orange ring in that photograph is light from gas on the far side of the black hole, bent around the photon sphere and brought to us along curved paths. The shadow inside the ring is not the horizon itself, but is larger, because the bending of light effectively magnifies the dark region. The relationship is precise, and it is what allowed the imaging team to compare what they saw against what the theory predicted. A little further out, for a black hole that is rotating, lies a stranger region still, called the ergosphere. Most black holes do rotate, because the stars that formed them rotated, and the spin is preserved through the collapse and concentrated into the much smaller object that remains, just as a spinning ice skater pulling in her arms turns faster. The mathematics of a rotating black hole was not worked out until 1963 by a New Zealand mathematician named Roy Kerr, who found a second exact solution to Einstein's equations, more complicated than Schwarzschild's but more relevant to the real world. In Kerr's solution, the rotation drags the space around the black hole with it, twisting the fabric like batter being stirred. The region inside which this dragging is strong enough that nothing, not even light, can stand still relative to the distant stars is the ergosphere. Within it, you are not yet doomed the way you are within the horizon. You can still escape. But you cannot resist being whirled along with the spinning black hole's coil of dragged space. It is the only place in nature where the rotation of an object literally carries the surrounding space around with it. The ergosphere has one remarkable property that becomes important when we ask how black holes can power some of the brightest things in the universe. Energy can be extracted from a rotating black hole's spin. A particle entering the ergosphere can be made to split, with one piece falling into the hole on a path that subtracts from its rotation, and the other piece flying out carrying away more energy than the original particle brought in. The extra energy comes from the rotation of the black hole itself, which is gradually slowed by the process. In the real universe, this is how matter falling toward a spinning black hole can sometimes be launched outward at very nearly the speed of light, forming the kind of relativistic jet that Heber Curtis saw projecting from the center of M87 a century before anyone knew what was driving it. A black hole, despite its name, can be one of the most efficient engines for converting mass into outgoing light and matter that exists in nature. Up to about 40% of the rest energy of material falling toward a spinning black hole can in principle be radiated away, far more than the less than 1% that nuclear fusion releases in a star. Between the photon sphere and the event horizon, anything orbiting the black hole has run out of stable paths. There is an innermost stable circular orbit at 3 Schwarzschild radii for a non-rotating black hole, closer in for a spinning one, And inside that radius, any orbit decays inward, no matter how fast you are moving. Material spiraling into a real black hole, drawn in from a companion star or a passing cloud, piles up just outside this radius into a swirling disk, heated by friction to millions of degrees and shining in X-rays as it gradually falls inward and over the inner edge. The disk is the part we usually see. It is the light from this disk that betrayed the first black hole astronomers ever became confident about. What about falling in? The answer depends sharply on how massive the black hole is. For a stellar mass black hole, only a few times heavier than the Sun, the gravitational field near the horizon changes so steeply with distance that the difference in pull between your feet and your head, were you falling in feet first, would be enormous. The technical name for this is a tidal force, the same effect by which the moon raises tides on the Earth, magnified almost without limit by the smaller object's compactness. Long before you reach the horizon of a stellar black hole, the tidal forces would stretch you out into a thin filament. The American physicist Kip Thorne coined a half-comical name for this, spaghettification, and the term has stuck because it captures the geometry exactly. For a supermassive black hole, the tidal forces at the horizon are much gentler, because the horizon is so much larger and the field varies more slowly across it. You could pass through the event horizon of M87 star without immediately being torn apart. The spaghettification would still come, eventually, as you fell further toward the center. But you would have time inside the horizon to notice what was happening, in a place from which no notice could ever return. What you would see, looking outward as you fell, is among the strangest pictures the theory paints. The universe behind you would appear distorted into a brilliant compressed disk overhead, the light of all the distant stars bent and concentrated into a narrowing window. Blue shifted as gravitational time dilation runs the rates of distant clocks faster than your own. The view would not go dark. It would, in some sense, brighten. The boundary itself, if you tried to look down at it, would not be visible as a surface, because nothing crosses it that could send a signal back. The black hole has no inside one can see from outside, and no outside one can see from inside in any useful way. We must also reckon with what is not at the center, despite the equation's insistence. The singularity, that point of infinite density to which Einstein's theory says everything must fall, is widely understood by physicists to be a placeholder, a sign that the description has broken down. Inside the horizon, where gravity becomes overwhelmingly strong on smaller and smaller scales, the quantum nature of matter must matter, and the marriage of quantum physics with general relativity is the great unfinished problem of theoretical physics. Whatever sits at the heart of a real black hole, it is almost certainly not literally infinite. It is something else, something we do not yet have the mathematics to describe. The honest position is to admit that the deepest interior of these objects is currently outside our understanding, in the same way that the interior of an atomic nucleus was outside the understanding of 19th century physics. The horizon, however, and the region around it, and the way it interacts with everything outside, are within our reach, and rather precisely so. There is, finally, a feature of these objects that comes as a surprise the first time one hears it, because it runs against the intuition that complicated things must have complicated descriptions. A black hole, viewed from outside, is one of the simplest objects in physics. To describe a star, you have to specify its size, its composition, the distribution of its temperature, its rotation, the structure of its magnetic field, the abundance of every element in it, the patterns of motion in its atmosphere. To describe a black hole completely from the outside, you need exactly 3 numbers: its mass, its spin, and its electric charge. That is all. Whatever fell in to make it: hydrogen, lead, encyclopedias, dust, neutron stars. The memory of any of that content vanishes through the horizon, and what remains is the same kind of object regardless. Two black holes of the same mass and spin are externally indistinguishable. This result is known as the no-hair theorem, a phrase coined by John Wheeler again, and it has a curious consequence. It means that the photograph of M87 star could be predicted in advance from a tiny number of properties because there is almost nothing else about a black hole to predict. The simplicity is not laziness in the theory. It is a deep statement about what a black hole is. An object that has been so completely reduced by collapse that almost everything that distinguished its source has been erased. All of this, in the early 1960s, was still theoretical. The Kerr solution had just been found. The Oppenheimer-Snyder calculation was being rediscovered. The geometry of horizons and singularities was being clarified in long technical papers by Roger Penrose and others. Yet no one had ever observed an object and confidently said, "That is a black hole." The case rested entirely on a chain of reasoning from the equations, and a great many astronomers continued to suspect that nature, somehow, would never actually produce such a thing. What was needed was a piece of sky with a real, observable peculiarity in it, a place where the gravity of something dark and dense made itself known by what it did to a neighbor that could still shine. That place was waiting, 300 years after Newton, in the constellation of the Swan. The constellation is Cygnus, the Swan, a long cross of bright stars laid along the summer Milky Way, with the bright star Deneb at its tail. On the 18th of June, 1964, a small rocket launched from White Sands in New Mexico carried an X-ray detector above the atmosphere for a flight lasting only a few minutes, the kind of brief ascent that was, in the early days of X-ray astronomy, the only way to see the X-ray sky at all. Earth's atmosphere is opaque to X-rays, which is fortunate for us biologically and inconvenient for astronomy, so the detectors had to be carried above it, and in those years, they could only be carried for the duration of a sounding rocket's parabolic arc. During that one flight, the instruments registered a strong X-ray source in the direction of Cygnus. It became, in the catalog, the first such source identified there, and was named Cygnus X1. For a few years, no one knew quite what to make of it. X-ray sources were a new category of object, and the resolution of the early detectors was poor enough that the position of Cygnus X1 on the sky was known only to within a circle large enough to contain hundreds of ordinary stars. Through the late 1960s, astronomers narrowed that circle, and in 1971, a new generation of detectors carried aboard a satellite called Uhuru, the Swahili word for freedom, launched from Kenya by the United States in honor of the country that hosted it, refined the position further. By that point, the X-ray emission was found to vary on extremely short timescales, flickering on millisecond intervals. This is itself a powerful clue. A source that brightens and dims that quickly cannot be very large. The size of any emitting region is limited by how long light takes to cross it, because variations cannot be synchronized across a region faster than light can travel within it. Millisecond flickers mean an emitting region only a few hundred kilometers across, which is preposterously small for anything visible at interstellar distances. Whatever Cygnus X1 was, it was tiny and very hot. When the X-ray position was pinned down precisely enough to identify the optical companion, astronomers found something striking. The source coincided with a bright blue supergiant star, catalogued as HDE 226868, sitting some 6,000 light-years away. The supergiant itself was not the X-ray source. It was a large, hot, ordinary star, of the kind that emits visible light and ultraviolet, not the kind that throws off vast amounts of X-rays. But the supergiant turned out to be in a tight binary orbit with an unseen companion, completing one revolution every 5.5 days. By measuring the wobble of the supergiant, the Doppler shifting of its light as it swung first toward us and then away, astronomers could weigh the dark partner. The mass came out around 15 times that of the Sun. Whatever was dragging the supergiant around had to weigh at least many solar masses, and yet was emitting no light of its own at any wavelength the optical telescopes could see. Only the brilliant flickering X-rays produced, as gas streaming off the supergiant, fell toward it. The mechanism of that streaming is itself a small piece of the story worth picturing concretely. The supergiant in this system, a star nearly 20 times the mass of the Sun and many times its radius, is so close to its dark partner that it does not orbit at a comfortable distance. The gravity of the unseen companion reaches across the gap and pulls outward on the supergiant's outer layers, drawing material off the star in much the same way ocean water is pulled into a tidal bulge, but vastly more strongly. Material from the supergiant is drawn away in a continuous stream, leaving the star and spiraling toward the compact object. The stream cannot fall in directly. It carries angular momentum from the orbital motion, and that angular momentum forces it into a flat rotating disk before it can reach the center. Within the disk, gas at slightly different radii rubs against itself, and the friction heats it to extraordinary temperatures, hotter than the surface of any star, hot enough to glow not in visible light, but in X-rays. The X-rays we detected from White Sands in 1964 were the screams of that gas in its last few hundred kilometers before crossing the event horizon. Once across, it is gone. The disk simply ends at its inner edge, and the X-ray light from there carries the final report. That combination is the signature. A compact object, far too small for any ordinary star, far too massive for any neutron star, hidden, drawing gas off a luminous companion, the gas piling into an accretion disk and heated as it spiraled inward, the disk shining in X-rays from material reaching temperatures of millions of degrees in its final approach. Working through the alternatives systematically, no other candidate could be made to fit. A white dwarf could not have been so heavy. A neutron star could not have been so heavy either, given the upper limit on neutron star masses we discussed. There was, by the early 1970s, no remaining honest interpretation other than a black hole. The case was so good that in 1974, two of the leading physicists working on these questions made a famous private bet about it. Stephen Hawking, working at Cambridge, wagered against Kip Thorne, working at Caltech, that Cygnus X1 was not in fact a black hole. The wager was structured peculiarly. Hawking wrote in a clause that since he had devoted so much of his professional life to studying black holes and would suffer professionally if they did not exist, his bet against Cygnus X1 amounted to an insurance policy. Either he was wrong, in which case the black hole community had been vindicated and he would be among those celebrating, or he was right, and Cygnus X1 turned out to be something else, in which case he would at least win the wager and gain some compensation for the disappointment. The prize, if Hawking lost, was a 4-year subscription to the magazine Private Eye. If he won, Thorne would receive a 1-year subscription to Penthouse, which Hawking had specified to annoy Thorne's wife. The bet, written on paper and signed, hung framed on Hawking's office wall for the next 16 years. In 1990, with the evidence overwhelming and the case for Cygnus X1 essentially closed, Hawking conceded. He traveled to Thorne's office and thumbprinted his name on the framed document, since the disease that had been slowly paralyzing him by then prevented him from signing, and the magazine's subscription was duly arranged. Hawking remarked that he had at last lost a bet on a black hole question, having previously won several smaller ones, and his colleagues took this as the formal moment at which black holes had become uncontroversial in the field. The first black hole had been admitted into the catalog. The route by which the field reached that consensus is worth pausing on, because it was indirect in a way that turns out to be characteristic. No one had seen Cygnus X1 itself. They had inferred it. They had measured the orbit and motion of an ordinary star, calculated the mass of its invisible partner, looked at the X-rays produced by gas falling toward that partner, calculated the conditions necessary to produce X-rays with those properties, and ruled out, one by one, every alternative explanation. The black hole was confirmed by elimination of everything it could not be. That kind of confirmation can sound weaker than direct sighting, but it is in fact the standard method by which physics establishes the existence of objects too small or too far to be photographed, the method that confirmed the existence of atoms, of distant planets, of dark matter. You do not need to see the thing if you can measure its gravity and rule out everything else. Through the 1970s and 80s, many more candidates joined Cygnus X1. Some were similar, X-ray binaries in which a stellar mass black hole pulled material off a companion, scattered throughout our galaxy. Others were strange new categories entirely. Quasars, the brilliant pinpoints of light at the centers of distant galaxies, first cataloged in the 1960s as quasi-stellar objects because they looked like stars, but had spectra suggesting impossible distances, were eventually identified as the active centers of galaxies, powered by supermassive black holes drawing in matter at prodigious rates. Some of these supermassive holes were found to contain billions of times the Sun's mass, in the centers of galaxies far across the universe. The objects that physics had spent decades arguing might not exist turned out to be everywhere we were able to look. Beneath the catalog, though, ran an idea Hawking himself had introduced in the same years he made the bet, an idea so strange that for a while many of his colleagues did not believe it. Until the early 1970s, a black hole was understood to be exactly what its name suggested. It absorbed everything and emitted nothing. It only grew. But Hawking, applying quantum physics to the region just outside the horizon, calculated in 1974 that black holes are not entirely black. They radiate, faintly, a thermal glow with a precisely defined temperature inversely related to their mass. The radiation comes from the way the quantum vacuum behaves in curved space. And it has the consequence that, given enough time, a black hole left to itself with nothing to feed on will gradually evaporate, returning its mass and energy to the surrounding universe as a slow drizzle of particles and light. The timescales for this are absurdly long. A black hole of stellar mass would take something on the order of 10 to the 67 years to evaporate, vastly longer than the present age of the universe, which is a mere 10 to the 10th. But the calculation is mathematically rigorous, and it links three of the most foundational theories in physics, gravity, quantum mechanics, and thermodynamics in a single result that no one had anticipated. It is now called Hawking radiation, and it is one of the deepest predictions theoretical physics has made in the last 50 years, even though it has never been observed, because the radiation from any real astrophysical black hole is far too faint to detect. The fact that we have not seen Hawking radiation does not mean we are uncertain of it. It is implied so directly by the combination of established theories that almost no one doubts its reality. But it leaves a paradox of its own. If a black hole eventually evaporates, what happens to the information about everything that fell into it? The no-hair theorem said that the outside of a black hole carries only mass, spin, and charge. If the hole radiates away its entire mass as featureless thermal photons, then the detailed information about whatever fell in, the patterns of atoms, the structure of stars, the imprint of any particular history, appears to be permanently lost. Quantum physics, however, ordinarily insists that information cannot truly be destroyed. That conflict is known as the black hole information paradox, and 40 years of work has not yet resolved it. It is the place where the deepest questions about the nature of these objects, and indeed about the foundations of physics, are now being asked. We will not chase it further here. It is enough to know that the things that began their existence as a peculiarity in Schwarzschild's wartime calculation have, in the half-century since they were first reluctantly accepted as real, become the subject around which much of fundamental physics now turns. Cygnus X1 was the first. Through the 1970s and 80s, it remained the cleanest example, the textbook case. But the most spectacular evidence, the kind that does not rely on inferring an invisible partner from the motion of a visible one, but instead lets you watch a star perform a complete loop around something dark and time the loop to within seconds, did not come from Cygnus or from any other distant binary. It came from the very heart of our own galaxy, from a region of sky so crowded with stars and so wreathed in obscuring dust that it took 30 years of patient observation by two competing teams working at the world's largest telescopes to extract a single clean measurement. What they found, in the end, was an object weighing 4 million suns in a volume smaller than our own solar system. And one of the stars whose motion proved it was a single, swift point of light, designated S2. The center of our galaxy sits in the direction of the constellation Sagittarius, low in the southern sky from the northern hemisphere, where the densest band of the summer Milky Way thickens toward a bulge of old stars. From the Earth, it lies some 26,000 light-years away. That distance is small by the standards of this story. M87 was 55 million light-years out. The binary system in Cygnus was 6,000. The galactic center is closer than either, but it is far harder to see, because the line of sight between us and it passes through the dustiest, most crowded plane of our own galaxy. In ordinary visible light, the heart of our home is hidden behind thick curtains of interstellar dust that absorb the light of the stars beyond. Astronomers had suspected since the 1930s that something unusual lived in that obscured region. But for decades, they could not see clearly enough to say what. Then in 1974, two radio astronomers using a long baseline interferometer in West Virginia, Bruce Balick and Robert Brown, identified a peculiar compact radio source at the precise center of the galaxy, very small and very bright. They named it Sagittarius A star, with the same star symbol used a century later for M87 star, to distinguish this particular point source from the broader region of radio emission around it. It was clearly something out of the ordinary. The source was extremely compact, smaller than any star, and it sat very nearly motionless at the dynamical center of the Milky Way, the point that everything else in the galaxy was rotating around. The suspicion took shape that it might be a supermassive black hole, similar to but smaller than the engines of distant quasars, sitting silently at the heart of our own galaxy. But suspicion is not measurement. To go further, astronomers needed to see what the stars closest to Sagittarius A star were doing. This is where the technology of the late 20th century finally caught up with the question. Two new tools made the measurement possible. The first was infrared astronomy. Infrared light, unlike visible light, can penetrate the curtain of interstellar dust, because the dust grains are too small to scatter the longer infrared wavelengths effectively. Telescopes equipped to see in the infrared could see through the dust and pick out the individual stars crowded around the galactic center. The second tool was a technique called adaptive optics. The Earth's atmosphere is in constant turbulent motion, and that motion blurs the images formed by any ground-based telescope, smearing every star into a wobbling, fuzzy disk. Adaptive optics fights back. A mirror in the telescope's light path is flexed many hundreds of times per second by a network of computer-controlled actuators, deforming its shape in precisely the pattern needed to cancel the atmospheric distortion. The result is that ground-based images, in some bands, can rival the sharpness of telescopes in space at a fraction of the cost. In the early 1990s, two teams set out to use these tools to track the motions of stars near Sagittarius A star. One was led by Reinhard Genzel, a German astrophysicist working at the Max Planck Institute in Garching, using the telescopes of the European Southern Observatory in Chile. The other was led by Andrea Ghez, an American astrophysicist at the University of California, Los Angeles, using the Keck telescopes on Mauna Kea in Hawaii. The two groups were not collaborators, but competitors, working independently on opposite sides of the planet, observing the same patch of sky with different instruments and different software. The competition was sharp enough that the field has consistently spoken of the two efforts as parallel rather than joint. It would prove to be an unusually productive form of rivalry, because it meant that every claim from one group would be checked against the same observations made independently by the other. The stars they tracked were the closest ones they could see to the central radio source, a swarm of about 100 massive young stars catalogued individually and labeled in Genzel's group's nomenclature with the letter S followed by a number. The existence of these stars is itself a small mystery the field has not entirely resolved. The S cluster is made of hot, blue, massive young stars, the kind of stars that live only a few million years before exploding. They are crowded into a region around the central black hole, where, by ordinary reasoning, no star should be able to form, because the tidal gravity of the central object should tear apart any gas cloud trying to collapse into a star long before it could reach stellar density. And yet the stars are there, plainly young, plainly bright. They cannot have wandered in from elsewhere in their present form, because the trip would have taken longer than they have lived. Astronomers still debate exactly how they got there. They are sometimes called the paradox of youth, and they are one of several reminders that the immediate environment of a supermassive black hole, even in our own galaxy, is a regime the textbooks do not yet fully describe. The brightest and most useful of them, for reasons of its proximity and orbital period, was given the designation S2. It is a hot blue star about 15 times the mass of the Sun and a great deal brighter, sitting just a few light days from the central source at its closest approach. From year to year, as the teams gathered images, this star and its neighbors were seen to be in motion against the background. They were not orbiting calmly, they were racing. The patience required is hard to convey. A single orbit of S2, the star with the shortest period in the swarm, takes about 16 years. Patient observation, in this case, meant returning to the telescope, year after year, to photograph the same field, building up a track of measurements that would eventually trace the star's full path. Over the course of the 1990s and into the 2000s, both groups accumulated data points slowly. The star moved, the curves bent, the orbit emerged from the noise. There is a particular quality to this kind of science that deserves to be noted, because it is not the science that makes headlines. Genzel and Gez were both in their early 30s when they started the observations. They were in their 60s when the Nobel Committee called. The careers of the graduate students who joined them in 1993 or 94 ended, in some cases, while the orbit was still being traced. The technical staff at the observatories rotated through. The telescope optics were rebuilt and re-aimed. The detectors were upgraded twice, and through it all, the same patch of sky a few light days across at the center of the Milky Way had to be visited every few months, and the brightnesses and positions of a small set of stars recorded. Most of those nights, nothing remarkable happened. The data accumulated grain by grain. The story of black holes confirmed by observation is not, mostly, the story of bright sudden discoveries. It is the story of long campaigns conducted by people who chose a question at the beginning of their working lives and were still working on it at the end. By the year 2002, S2 had reached its closest approach to the central source, a point called Pericenter, and was found to be moving there at over 7,000 kilometers per second, more than 2% of the speed of light, the fastest motion ever measured for a star bound to another body. It then swung around the dark central object and began the long climb back to its more distant point of the orbit. When the orbit was fully traced and the geometry analyzed, the conclusion was unavoidable. To hold S2 on its observed path, with its observed speed, the central object had to contain about 4 million times the mass of the Sun. And because S2 came so close to it without colliding with anything, the entire 4 million solar masses had to fit inside a region smaller than the orbit of Pericenter, which is to say, smaller than the orbit of Pluto in our own solar system. There is no known object of any kind, other than a black hole, that can pack 4 million suns into such a volume? By the early 2000s, the answer was effectively settled, and through the following 2 decades it was sharpened further. The Nobel Prize for the work was awarded in 2020 to Genzel and Gez, jointly with Roger Penrose, for the theoretical and observational establishment that a black hole sits at the center of our galaxy. In 2018, just before the EHT photographed M87 star, S2 reached pericenter again, completing the cycle that had begun in the early 1990s. This time, with better instruments and 3 additional decades of orbital data, the measurements were sharp enough to test something more delicate than just the mass. Einstein's theory predicts that the orbit of a star moving so deeply in the gravitational field of a black hole should not be a closed ellipse. It should precess, the same way Mercury's orbit precesses around the Sun, but much more dramatically, because the gravity is so much stronger. Genzel's team and Gez's team both detected the predicted precession in S2's orbit, and the size of the effect matched general relativity's prediction to within a few percent. The same theory that had explained a tiny anomaly in Mercury's orbit 103 years earlier was, with the same equations and no adjustments, also explaining the motion of a star around a 4 million solar mass black hole at the heart of our own galaxy. It is worth pausing on what this means. Mercury's anomaly, measured in 1915, was 43 seconds of arc per century. The precession of S2's orbit, measured a century later, was many degrees in a single passage. The phenomenon is the same. The strength differs by a factor of millions, because the gravity at S2's pericenter is vastly stronger than the gravity at Mercury's. Einstein's theory, written for a different scale and confirmed against a small effect, scales up perfectly to a scale he never imagined. There are not separate physics for stars and for black holes. There is one description of gravity, one set of equations, and they continue to work when you push them into regimes where common sense suggests they should break. Sagittarius. A star is not a quiet object. It is small as supermassive black holes go, only about 1,000th the mass of the one in M87. But 4 million suns is still 4 million suns, and material does occasionally fall toward it. From time to time, astronomers have seen brief X-ray flares from the central region, the signatures of small parcels of gas being heated as they spiral in. The Event Horizon Telescope, the same array of dishes that photographed M87 star, also turned its attention to Sagittarius A star. And in 2022, the team announced their second photograph, this time of the black hole at the center of our own galaxy. The image looked recognizably similar to the M87 one, a ring of light around a dark shadow, the shadow about the same angular size on the sky despite the source being smaller, because we are so much closer to it. The two pictures together established something striking, that 2 black holes separated by 55 million light years and by a factor of more than 1,000 in mass look, to within the limits of what the instruments can resolve, like the same kind of thing. The no-hair simplicity, predicted in the equations, was being confirmed in photographs. To track S2 was, in a sense, to discover that something most of physics had grudgingly come to believe in the abstract was a real object in our own sky, only a few tens of thousands of light years away, with one nearby star whirling around it on a measurable schedule. That is one of the cleanest discoveries the field has produced. But it confirmed only that one of these things sits at the center of our galaxy. It said nothing about black holes that are not surrounded by orbiting stars, black holes wandering between galaxies, black holes formed in the deaths of stars elsewhere in our galaxy, black holes that have no luminous companion at all. To detect those, a completely different sense was needed. Not the sight of light, but the feel of a vibration. And in 1915, the same year Schwarzschild was solving the equations at the front, Einstein had quietly predicted that this vibration existed. The prediction sat in a short paper Einstein published in 1916, only a few months after he had completed the full theory. If mass curves space, he reasoned, then mass that is moving, accelerating, or otherwise rearranging itself ought to produce changes in the curvature, and those changes ought not to be felt everywhere at once. They ought to propagate outward, like ripples spreading on the surface of a pond when a stone is thrown in. The ripples would travel at the speed of light, would stretch and squeeze the space they passed through in a precise pattern, and would carry energy away from whatever produced them. He called them gravitational waves. They were a direct consequence of the theory. They were also, he calculated, so unimaginably faint that he believed they would never be measured. His skepticism on that last point was thoroughly justified. The strain a gravitational wave imposes on the space it crosses is fantastically small. Even for the most violent astrophysical events imaginable, the wave reaching Earth would change distances by a factor of about 1 part in 10 to the 21st. To put that in concrete terms, it would change the length of an object the size of the Earth by less than the diameter of a single atomic nucleus. Most physicists in the early 20th century, including Einstein himself at various moments, thought the effect was so tiny as to be permanently out of reach. Through the 1930s and 40s, Einstein even came briefly to doubt that the waves were real in any meaningful sense, wondering whether they might be a mathematical artifact rather than a physical phenomenon. It took until the late 1950s for the theoretical community to settle the question and confirm that gravitational waves were genuine, carried real energy, and could in principle be detected by an instrument exquisitely sensitive enough to register the squeeze and stretch they imposed. The practical effort to build such an instrument began modestly in the 1960s with a series of cylindrical aluminum bar detectors developed by Joseph Weber at the University of Maryland. The idea was that a passing gravitational wave would ring the bar like a tuning fork, by an amount potentially measurable with sensitive electronics. Weber reported detections in the late 60s and early 70s. The reports were not confirmed by other groups, and the consensus that eventually settled was that the bars had not been sensitive enough to detect what Weber believed they had detected. But the effort had served a purpose. It had convinced a generation of physicists that the problem was at least worth taking seriously, and it had clarified, by failing, how difficult any real detection would have to be. A different concept emerged from this experience, championed in the United States by Rainer Weiss at the Massachusetts Institute of Technology, by Kip Thorne at Caltech, and by Ronald Drever at Glasgow and later Caltech, and parallel efforts elsewhere. Instead of trying to make a single solid object vibrate, the new idea was to measure the distance between two free-hanging mirrors using laser light. A passing gravitational wave would stretch the distance one way and squeeze it the other, alternately in a known pattern. If you sent a laser beam back and forth between the mirrors and compared its travel time along one direction against another at right angles to it, the wave's signature would appear as a tiny difference in those travel times. The geometry that emerged was an L shape, two long arms meeting at a right angle, with mirrors at the far ends, a laser at the corner sending light down each arm and measuring how the returning beams interfered with one another. The technology to make this work did not really exist in the 1970s, but the people involved persuaded the United States National Science Foundation to fund it anyway, in what became, for a long time, the largest single scientific investment the agency had ever made. The instrument they eventually built is called LIGO, the Laser Interferometer Gravitational Wave Observatory. There are two of them, identical in design, separated by 3,000 kilometers, one at Livingston in Louisiana and one at Hanford in Washington State. Each consists of a vacuum tunnel 4 kilometers long in each of two perpendicular arms, holding mirrors suspended on quartz fibers, isolated from the seismic motion of the ground by elaborate networks of pendulums and damping systems, with a stabilized laser beam circulating along each arm. The detectors had to be sensitive enough to measure changes in length much smaller than the diameter of a single proton, across arms 4 kilometers long. The technical achievement that went into that, in vibration isolation, in laser stability, in the manufacture of the mirrors themselves, occupied thousands of physicists and engineers across decades. The first version of LIGO, completed in the early 2000s, ran for several years without detecting anything. This was not a failure. The first version was, broadly, expected to be at the edge of what its design could see, with the hope that a major upgrade then in development would push the sensitivity over the threshold. The detectors were taken offline, rebuilt with substantially improved hardware, and brought back online in 2015 as advanced LIGO. The sensitivity gain was about a factor of 10 in strain, which corresponds to a factor of 1,000 in the volume of space accessible to the instrument. Whatever was out there making gravitational waves, advanced LIGO would see 1,000 times more of it than the first version had been able to. Engineering runs began in late August of 2015. The official first observing run was scheduled to begin on the 18th of September. On the 14th of September, at 5:51 in the morning Eastern Time, before the instrument had even formally started looking, a signal arrived. It hit the detector in Livingston, Louisiana first, and 7/1,000ths of a second later it arrived at the one in Hanford, Washington, having crossed the United States in the intervening interval. The signal lasted about 2/10ths of a second. It was a rising tone, climbing from about 35 oscillations per second up to 250, accelerating and tightening, and then cutting off abruptly. In the data plots produced by the analysis software, it had a characteristic shape, swept upward in frequency and amplitude, called by gravitational wave physicists a chirp. The reaction at the two collaborations was, by all accounts, one of cautious astonishment. The signal was so clean and so much louder than expected that the first response of many in the team was to suspect a hardware fault, a software glitch, or an injection from one of the test signals the collaboration regularly used to keep the analysis pipelines honest. An entire investigation went into checking every possibility. The blind injections were ruled out. The instruments were healthy. The signal had arrived at the two detectors with the correct time delay to be coming from outside the Earth, from a point in the southern sky between the constellations Mensa and Reticulum. It was real, and it was what they had built the instruments to look for, only louder and at higher frequencies than anyone had quite dared to expect. When the chirp was analyzed against the catalog of theoretical waveforms, the source was identified with remarkable specificity. It was two black holes weighing 36 and 29 times the mass of the Sun in the final fractions of a second of a long inspiral that had brought them down to within a few hundred kilometers of one another. They were moving at more than half the speed of light. They merged into a single, larger black hole of about 62 solar masses. The three missing solar masses, the difference between the input masses and the final mass, had been radiated away as gravitational waves. In the last fraction of that second, the merger had radiated power exceeding the total light output of every star in the observable universe combined. None of that power came out as light. It came out as a ripple in the shape of space itself, which traveled outward across the universe for 1.33 billion years and finally arrived at two L-shaped vacuum tunnels on the surface of a small planet that had only recently developed instruments sensitive enough to feel it. The shape of the chirp itself can be read, with a little patience, like a diary of the final moments of the merger. A pair of black holes orbiting one another emits gravitational waves continuously, but the waves carry away energy, and as the energy is lost, the pair spirals slowly closer together, the orbit tightening like a slowly winding spring. The closer they get, the faster they orbit, and the faster they orbit, the more strongly they radiate, in a feedback that runs away in the final fraction of a second. The rising pitch of the chirp is the rising frequency of the orbital motion. As the holes close in on each other, a frequency that began at 35 orbits per second when LIGO first detected it and climbed to 250 orbits per second in the final eye blink. The cutoff at the top of the rise is the merger itself, when the two horizons touch and become one. For an instant, the combined object is grotesquely distorted, ringing like a bell, and the wave includes a final brief signature called the ring down, in which the new black hole settles into the smooth Kerr geometry it will hold forever afterward. All of this happened in 0.2 of a second, after a courtship that had probably lasted hundreds of millions of years. The announcement was made on the 11th of February 2016 after 5 months of careful checking. It was, even by the standards of dramatic scientific announcements, a remarkable one. A century after Einstein had predicted gravitational waves and judged them undetectable, his prediction had been confirmed by direct measurement, and the source was a kind of object whose existence he had also predicted on paper and had himself doubted. The Nobel Prize for the work was awarded in 2017 to Weiss, Thorne, and Barry Barish, who had served as the project's director through the long years of construction. Since then, the detectors have run, with upgrades and pauses, and the catalog of gravitational wave detections has grown rapidly. By the early 2020s, the count was past 100 merger events, with the rate accelerating as further improvements are made. Most have been black hole mergers like the first of various masses. Some have been mergers of two neutron stars, which produce gravitational waves, and also, unlike pure black hole mergers, emit visible light and other electromagnetic radiation that can be followed up by ordinary telescopes. One such event, in August of 2017, allowed astronomers for the first time to point optical telescopes at the location of a gravitational wave source within hours and watch the merger's afterglow in many wavelengths. A few of the detected events have been mysterious, mergers in mass ranges that should not be allowed by what we know about how black holes form. Each of these is a small new puzzle for theory. Two features of the LIGO results are worth dwelling on because they shape how the field now thinks about black holes. The first is that we now know black holes exist in pairs that eventually collide. Before 2015, theoretical work suggested they should, but no example had been seen. Now they are routine. The first merger detected was, in itself, a remarkable demonstration. It confirmed that black holes of stellar mass exist, that they pair up, that they spiral together by losing energy to gravitational waves over millions or billions of years, that they merge, and that the merged remnant settles down into a Kerr black hole, obeying the same laws Roy Kerr had written out for an isolated rotating black hole in 1963. Each one of those pieces was, before LIGO, an inference. Each one is now an observed fact. The second feature is more subtle and perhaps more important. The waveform of a gravitational wave depends sensitively on the geometry of the spacetime through which the wave is generated. A merger of black holes is a moving region of extreme curvature, in which the field equations are doing their most strenuous work. Comparing the observed waveforms against the predictions of general relativity is therefore the strongest test of the theory ever performed, in the most demanding regime it has ever been pushed into. The matches so far are extraordinarily good. The theory, written by a patent clerk in Bern in 1915 and presented to the Berlin Academy that November, has continued to predict, with no adjustment and no fitting, the precise shape of the ripples produced by the collisions of objects whose existence it implied and whose discovery it took most of a century to bring about. It is one of the most remarkable success stories in the history of any branch of science. And so the case, by the end of the second decade of the 21st century, was effectively closed in three independent ways at once. The orbit of S2 had shown a 4 million solar mass black hole at the center of our galaxy. LIGO had recorded the collisions of stellar mass black holes throughout the local universe. And the EHT had produced, after years of patient effort, a photograph of the bright ring around a 6.5 billion solar mass black hole at the heart of M87. Each piece confirmed the others. The mathematics of 1915 had become the observed astronomy of the present. What remained in this account was the story of how that final image was actually built by an international team working for nearly a decade, and of the unusual precautions they took to make sure the picture they wanted to see was the same picture the data actually contained. The Event Horizon Telescope was not built in the usual sense. It was assembled, conceptually, out of telescopes that already existed and were already doing other work. The dishes that had been mentioned earlier in passing, in Hawaii, in Arizona, in Mexico, in Chile, in Spain, and at the South Pole, were not constructed for the project. They were independent observatories with their own staff, their own scientific programs, their own funding agencies, and their own scheduling priorities. What the EHT team had to do, over more than a decade of preparation, was persuade all of these observatories to point at the same targets on the same nights, to record their data using compatible hardware, to stamp it with synchronized atomic clock timestamps precise to a few trillionths of a second, and to ship the resulting drives to 2 correlation centers, one at the Haystack Observatory in Massachusetts, and one at the Max Planck Institute for Radio Astronomy in Bonn, Germany, where the recordings from different sites could be combined into a single coherent signal. The decade of preparation was substantially about whether this could be made to work at all. The technique of very long baseline interferometry was old. It had been used for decades on bright radio sources at long wavelengths. What the EHT was attempting was to push it to a shorter wavelength, around 1¼ millimeters, where the atmosphere becomes a serious obstacle and where the demands on synchronization and pointing precision become correspondingly harsher. Each step had to be solved before the next could be attempted. The hydrogen maser clocks at each site had to be characterized and matched. The atmospheric transparency at each site had to be modeled. The exact positions of each dish in space, including the small displacements caused by the Earth's tides, had to be tracked. And most importantly, the wide assortment of human institutions involved had to be brought into agreement about how the observations would be run and the data shared. The campaign that yielded the M87 image took place over 5 nights in April 2017, when the targets, M87 star in the Virgo cluster and Sagittarius A star at the center of our own galaxy, were both well placed for as many of the participating sites as possible. Each night the team waited for the weather at all sites simultaneously to be clear enough to observe. If even one dish was clouded out, the projected resolution of the entire array dropped sharply, because each new dish doubles the number of baselines, the pairs of dishes whose combined data contribute to the final reconstruction. They had to be lucky in many places at once. On a few of the planned nights, the conditions cooperated. By the end of the run, several thousand trillion bytes of raw data had been recorded onto a stack of hard drives at each site, ready to be shipped. Then came the part that took 2 more years. Combining the data was not a matter of running a standard image processing program. The pattern of dishes was sparse. The Earth's rotation, during the hours each target was observed, swept the dishes across the sky and effectively filled in more of the imaginary giant dish. But the filling was still incomplete. The team had a set of measurements that constrained the structure of the source without uniquely determining it. There were, mathematically, many possible images that all fit the recorded data within the uncertainties. The work of imaging consisted of finding the image or images that fit the data while also being consistent with general physical expectations, such as that the brightness of the source could not be negative. To choose among the possible images, the team faced a temptation that scientific imagination always has to guard against. They knew, going in, what an image of a black hole's shadow should look like, in broad outline. They had simulations from the theory. They were emotionally invested in a particular outcome. If they had simply found the image that best matched their theoretical expectation, the result would have been worthless, because any agreement with theory could have been seeded by the agreement itself, smuggled into the reconstruction by the very act of selecting it. The integrity of the announcement depended on showing that the image came from the data, not from the imagination of the people processing it. The mechanism they used to guarantee this is one of the quieter achievements of the project. They divided the imaging effort into 4 independent teams, working at 4 different institutions, and gave each team the same raw data, but instructed them not to communicate with one another about their methods or their results. Each team had to develop its own algorithm for reconstructing an image from the sparse measurements. 2 of the teams used what is called a maximum entropy method, which seeks the smoothest image consistent with the data. The other 2 used a different method, called clean, which builds up the image as a sum of point sources at successively refined positions. The 4 teams worked in isolation for 7 weeks. Only when they had each produced their best image did they put the results next to one another and look. The meeting at which this happened was held in July of 2018 at the Black Hole Initiative at Harvard. The 4 teams arrived with their results in sealed envelopes, in some accounts, or in the digital equivalent. Each was projected, one after another, onto a screen in front of the assembled group. There had been, in the months leading up to the meeting, considerable private anxiety. Each team had wondered whether their own image was an artifact of their particular method, whether they would be the one to show a ring that no one else had found, or no ring at all. The order in which the 4 were shown was not strategically chosen. The first image went up, then the second. By the third, the room understood what was happening. By the fourth, there was, by the account of several participants, applause. All 4 had produced rings. The rings had the same brightness, the same diameter, the same orientation, the same asymmetry around them. The agreement was not perfect down to the last pixel, because the methods made different choices in the spaces where the data was less constraining, but the gross features were so consistent across the 4 reconstructions that the team could be confident the ring was in the data, not in any team's preferences. It was at that moment, in a meeting room comparing 4 screens, that the discovery passed from hope to fact. The image was further checked against the theoretical predictions of general relativity. Given the mass of the central object, deduced from the speed of stars and gas in the galaxy, the theory specified the angular size of the shadow on the sky. The measured shadow matched the prediction to within the precision the instrument could provide. The diameter, the shape, the relative brightness around the ring, all of these properties followed from Schwarzschild's solution and Kerr's, modified for the particular geometry of our line of sight to M87. The agreement was, in the language scientific papers, reserved for cases where it might appear excessive, consistent. A great deal of public attention focused, in the immediate aftermath of the announcement, on a single member of the imaging team, a young computer scientist named Katie Booman, who had worked on one of the algorithms while a graduate student at MIT and had been photographed pressing her hands to her face in delighted disbelief as the first reconstructed image appeared on her laptop screen. The photograph circulated widely, and Booman became, for some weeks, the public face of the project. She herself was careful to emphasize, in interview after interview, that the work had been done by a collaboration of more than 200 people, that no single individual had produced the image, and that the photographic moment of her own reaction was simply that, a moment captured by chance. The work itself had been a collective undertaking over many years. The EHT did not stop with the M87 image. In 2022, as we have noted, the same array produced a second photograph, this time of Sagittarius A star at the center of our own galaxy. This was a harder target in some respects, because the gas around Sagittarius A star moves much more quickly than the gas around M87 star, completing orbits in minutes rather than days, so that the apparent brightness pattern shifts during a single night of observation in ways that have to be modeled and removed. The image, when it arrived, looked recognizably the same. A ring of light around a dark shadow the geometry consistent with a black hole of the mass that S2's orbit had implied. In 2024, the EHT released the first images of a magnetic field structure around M87 star, showing that the light from the ring is polarized in a pattern that traces the magnetic lines anchoring the relativistic jet that Heber Curtis had recorded in 1918. The straight ray of light he had described as connected to the nucleus more than a century earlier was now visible in its origin, the magnetic structure around the central black hole that focuses and accelerates the outflowing matter. A line of evidence first laid down in a Lick Observatory notebook had been completed in the same generation that put atomic clocks on telescopes scattered across the planet. What that polarization image showed in slightly more detail is the shape of the magnetic field in the very last region of space outside the horizon. The ring of light in the original 2019 photograph showed where the hot gas was. The polarization image revealed how that gas was organized, threaded by magnetic field lines that wind around the central object like the grooves of a vinyl record. Those field lines anchor in the rotating black hole and the disk, and as the black hole spins, they twist outward and act as the rails along which the jet of matter is launched. It is one of the most concrete demonstrations available of how the rotational energy of a black hole, the energy associated with its spin in the no-hair description, can drive structures larger than entire star clusters. The picture confirmed not just the existence of the central object, but a specific mechanism theorized in the 1970s by Roger Blanford and Roman Zanajek, for how a black hole's spin could be tapped to power the kind of jet that had been visible in M87 since 1918. It is worth stepping back at this point and noticing what has happened. A particular peculiarity in a calculation done by Karl Schwarzschild between artillery duties on the Russian front in 1915, a calculation he sent to Einstein as a small mathematical exercise, and that Einstein himself only reluctantly accepted as describing physical reality, has been confirmed by three completely different experimental methods in our own lifetime. The orbits of stars at the center of our galaxy have shown it. The ripples in space arriving at vacuum tunnels in Louisiana and Washington have shown it. The bent light from gas around the center of a galaxy 55 million light-years away has shown it. The objects exist. They behave exactly as the equations said they would. There is something quietly beautiful in this, beyond the technical achievement. A young man working at a patent office in Bern, dissatisfied with the explanation he had been given of why things fall, set himself a thought about a person in a sealed room, and from that thought, he constructed equations that described a universe in which space and time were not the fixed, empty backdrop they had been thought to be for 2,000 years. Those equations, when solved by other people in their gaps of time, predicted objects so strange that almost no one believed they could be real. Generations of physicists worked through the question of whether they could form in nature, against the resistance of their seniors and the limits of the technology of their time, and slowly came to the conclusion that they could. Telescopes and detectors capable of seeing them were built at vast cost by the people who succeeded those who had argued they were impossible. And then they were seen in three different ways, and the predictions of those original equations were confirmed in detail. This is what science can do when it is given a long enough horizon and people patient enough to walk it. The story has, in the end, the same shape as the orbit of S2, a long elliptical arc returning at last to its starting point. Einstein's prediction in 1915 that mass curves space and that the curvature can become so steep in some places that nothing crossing inward can come back out has been answered in 2019 by a photograph of exactly that curvature, captured by people most of whom were not yet born, when the field of black hole astrophysics began to take itself seriously, working with instruments most of whose builders did not live to see the first images. The science is genuinely difficult, and we have walked through it only at the level a single video can manage. But the central claim is now established beyond reasonable scientific doubt. There are objects in the sky from which no light can escape. They are made by gravity, exactly as Einstein's theory said they could be. They sit at the hearts of galaxies, and they wander in clusters between the stars. And one of them is 6.5 billion solar masses heavy and sits at the heart of a galaxy called M87. That is, in plain language, what black holes are and how we came to know them. If anything in this video has stayed with you, leave it a moment to settle before the next thing claims your attention. We will be back soon with another mystery from the sky.